exciting new chapter for us, nuclear chemistry. What is nuclear chemistry about? When I was a kid, I used to read about it in the encyclopedia, or I'd hear about it, and I'm like, is it a particle? Is it a wave? You know, when you're in 5th grade, you haven't taken Gen Chem yet. You don't know anything about all those things. All right, I actually have a reaction. So here's a typical type of nuclear reaction. And today what we're going to do is figure out what goes here, and then once we know what goes here, we'll be able to choose what's going on here. So here we go. Nuclear chemistry. Got the bomb in the background. Got these little movers and shakers in the world of nuclear chemistry. We got Becquerel, Curie, and Rutherford. And maybe you can tell me something about Rutherford. All right, first up, Becquerel. French physicist. He won a Nobel Prize in physics in 1903, and he shared that with Madame Curie. And he's the one who we say discovered radioactivity because he was working with photographic plates. X-rays had just been discovered, and you detect X-rays with photographic plates. And he did an experiment where he put uranium salts on a photographic plate. And so here is a photographic plate, and there's this black spot where he had
uranium.
Yeah, he left some uranium salts, and so that got him on the right path there. So Becquerel made the discovery that radioactivity could be used for medicine. He discovered this when he left a piece of radium in his vest pocket. Notice he had been burnt by it. Have you ever known anybody to get radiation therapy when they get cancer, and they basically get like a sunburn? In 1908, Becquerel was elected to the president of the Academy of Sciences, but he died on August 25th, 1908 at age 55 in France of a heart attack. But it was reported that he developed serious burns on his skin, likely from handling radioactive material. And this lady's fairly famous. So, you know, she worked with discovering radium, which people used to put everywhere. And despite Curie's fame as a scientist working for France, the public attitude tended towards xenophobia. What's that? Xenophobia. Well, over in France, they had this thing called the Dreyfus Affair. I won't talk about that. But it's filled false speculation that Curie was Jewish. During the French Academy of Science elections, he was vilified by the right-wing press as a foreigner and an atheist. And it was weird because she won the Nobel Prize and got all this fame, but she had a lot of detractors. And she must have survived all that. But then in 1911, well, before I go there, Madame Curie married a famous physicist, Pierre. And Pierre died in the street when he got hit by a carriage, a horse-drawn carriage. Carriage wheel went over his head. Horrible death. And Madame Curie became involved with former student of Pierre Curie. And he was a married man that had been estranged from his wife for a long time. And this resulted in a big press scandal, which was exploited by her academic opponents. There shouldn't be any opponents in academia. We're all working for knowledge. Actually, there's a little academic joke. Why are the battles in academia so fierce? And the punchline is because the stakes are so high. I find that entertaining. Curie was in her mid-40s then. She was 5 years older than this man and was misrepresented in the tabloids as being a foreign Jewish homewrecker. When the scandal broke out, she was away at a conference in Belgium. On her return, she found an angry mob in front of her house and had to seek refuge with her daughters in the home of a friend. Rutherford, what do we know about him?
Isn't he the person who actually created the atomic bomb, or am I misthinking?
You're probably thinking about Oppenheimer.
That's what I was thinking about. The wrong person.
Maybe he'll come up later. Yeah, Ernest Rutherford did the gold foil experiment, and he has been described as the father of nuclear physics and the greatest experimentalist since Michael Faraday. And you all know who Michael Faraday is, right? He used his constant, and he had a normal, successful, happy life. But this is the experiment. Rutherford saw that when he put some radioactivity in a box, this would be like a lead block with a cavity. So you put the radioactivity substance in the back, and radioactivity is shooting out in every direction, but it can be kind of focused in a beam. And they noticed that some rays were deflected up by a negative or by a positive electric field, and some were pulled down when they went through that electric field, and others went straight through. And by the amount of deflection, they could kind of figure out masses, and you see the beta ray, highly deflected, must be light, and that turned out to be high-speed electrons. Alpha particles turned out to be helium nuclei, and beta particles turned out to be high-speed electrons. And of course, the gamma rays, not affected by electric field, were X-rays. So recall that the nucleus is composed of 2 nucleons. Sounds like a Star Trek character, right? Protons and neutrons. The number of protons is the atomic number. The number of protons and neutrons together, which is effectively the mass, we call the mass number. And so here we say we have a carbon atom, and we say we have carbon-12, because there's other flavors of carbon besides carbon-12. Now when we have a nuclear equation, we say the number of nucleons is conserved.
So basically, both sides of the equation have to have the same number of neutrons and protons.
Right, so if we look at this, we see uranium-238, and then we look at thorium over there. It has a mass number of 234, and we see this alpha party, that helium nucleus, has a mass number of 4. Well, what does 4 and 234 sum up to?
238.
238. All right, thorium has an atomic number of 90. Helium, we say an atomic number of 2. And what does that sum up to? 92. So that's how you figure all these things out, and it's as easy as ABC. It's just...
They always have to add up to each other.
Nucleons are conserved. So here is alpha decay, which is loss of a helium nucleus. So here's the alpha particle. And here's what we just saw. 4 and 234 sum up to 238. 90 and 2 sum up to 92. Beta decay is loss of a beta particle. High energy electron. So here you learn something new. What is the mass number of electron? Call it 0 because it's like 5,000 times less massive than a proton or neutron. What's an electron's atomic number? Here's something new. A -1. That's how I kind of like to think of these. So we can say -1 and 0, or we can say beta. I like the electron. So here's iodine 131. It's got to be, if it's iodine, it has 53 protons. That gives its identity. Over here, I see an element with atomic number 54. Look up at the periodic table. You see it's right to the right of iodine is xenon. And so notice 0 and 131 sum up to 131. 54 and -1 sum up to 53. Here's something new. Positron emission. Some nuclei decay by emitting a positron. Positron is just like an electron, but opposite in charge. I like to call it antimatter. It's the antimatter of an electron. And so notice here's carbon-11. You've probably said, I've heard of carbon-14. You just told me most carbon was carbon-12. 1% of the carbon found on the Earth is carbon-13. So this thing really isn't happy. And so it undergoes a nuclear change. And it can turn itself into boron, boron-11, if it emits a positron. So we call this positron emission. Gamma emission is loss of an X-ray, which is a high energy radiation that almost always accompanies the loss of a nuclear particle. Here's this thing called electron capture. addition of an electron to a proton inside the nucleus of an atom is known as electron capture, or this thing called decay capture. The result of this process is that a proton is transformed into a neutron. Here's our nuclear symbol for a proton, and so -1 and 1 sum up to 0. You know, a neutron isn't a proton. We say atomic number is the number of protons, so the 0 should make sense. And this makes sense to me because I tell students at the beginning of Chem 1, where you see that the mass of a neutron is slightly larger than a proton, because a neutron is really just a disguised proton and electron hiding out as a neutron. So here are all these symbols for everything that could occur. All right, nuclear stability. Let's talk about that in a second. Let's just do this one. I say here's 20, here's 19. Yeah, this is a positron decay. I failed at summing up nucleons this morning. All right, let me just give you one more and then I'll let you go. All right, what about this one here?
Don't you have to lose, isn't it, electron?
Oh, it's looking electron there. Yeah, there's the missing nucleon. Right, so this would be electron capture. So next Monday, we'll do some more of these.